Hello everyone, welcome to Stat 479, Lecture 19, sorry. So we're in the last kind of couple of lectures of kind of key methodological content in this course. So the last module we're focusing on graphical models, and the last 3 or 4 lectures we focused on kind of defining the statistical model associated with graphical models, because it's kind of a new concept for a lot of you, because we're connecting this notion of a graph to kind of a multivariate distribution. And towards the end of the previous lecture, and what we're going to focus on for the next 2 lectures, is how we actually estimate the graphical model from data. So there's really 2 key components to this estimation, which we spoke about before. One is the parameter estimation. So if you know what the graph structure is, like, can you estimate the parameters of the graph? And the majority of today will focus on that. And then the more interesting, potentially, and more challenging question is, often in practice, the graph structure is not actually known. You just observe, kind of like, you have observations of your data, and then you want to estimate the graph structure from that data. And so that's going to be, as we spoke about in the previous lecture, that's a model selection type of problem rather than a parameter estimation problem. And we'll talk about kind of approaches to doing that, maybe towards the end of this lecture, and then in the final lecture, lecture 20. So just to recap on the statistical framework when we're talking about graphical models, and this is something we spoke about briefly at the end of the previous lecture. So here your data is like this kind of, you could think of it as an n by p matrix. So you have x1i up to xpi for I equals 1 to n. So here this is unsupervised data. There's no response y here. And so the statistical model here is a graphical model. And again, the way to just think about that is that you have a multivariate distribution with p variables, and you somehow encode the information in that distribution through a graph g equals VE. And then you take n independent samples from this multivariate distribution. So just to be clear, you have independence across the samples, but you don't have independence across the covariates. So it's very important to make that distinction here. Obviously, the graphical model means that there's dependence between the x1 through to xp's, but you're drawing independent samples from that. So the statistical model or graphical model, as we learned in the previous few lectures, is a little bit more challenging to define than what we've seen before. So we'll go through that briefly first. So there's two examples of graphical models that we've seen: the DAG model and the undirected graphical model. So for the DAG model, we have this graph g equals VE, where V is like the random variables x1 through to xp, and E is a set of directed edges. And then we had this important concept of parents, which is just all of the parents of xj, which kind of just means all of the nodes where there's an edge going from xk to xj, and it's very important that that direction is right. So it's an edge from xk to xj. And then there's a couple of ways we learned to characterize that. So the first one was through the factorization. So knowing the parents, you could kind of define the joint PDF in terms of the conditional PDFs of all of each of the p nodes given the parents of that nodes, and that defined the overall distribution. And then there was this nice connection between the graph structure and conditional independence. So as I mentioned right at the beginning, and as we've discussed throughout, the graph kind of represents conditional independences or dependences between different nodes. So there's a conditional independence between xj and xk given the parents of the 2 nodes, and you don't include those 2 nodes themselves. If and only if there's no edge between xj and xk in the graph E. And obviously the converse also holds. So if they're dependent, then there would be an edge between them, and that's kind of the way to connect the graph structure to the to the conditional independence. And we saw a couple of examples of that in the previous few slides, in the previous few lectures. So as I mentioned, there's and we're going to get to this notion of parameter estimation and then graph structure estimation. And that's where this notion of how we define parametric models is really important. And so in the case of DAGs, there's really one, we can define, because we have this nice factorization in terms of the conditional PDFs, we can kind of define we can define a parametric model by just considering like kind of conditional PDFs for each of the P nodes. So for J, the first one we saw in the case of normal was the structural equation model. So here it's a linear structural equation model, meaning that xj is just the, you just kind of like see it as a linear model in terms of the parents of xj plus some independent Gaussian noise. And we typically also added a mean term here, but that won't be of such great relevance here. And then you can generalize that if you don't have a kind of, normal or continuous data by using the GLM family. So you just write, essentially you write the xj as essentially just a GLM where your response is your xj and then your covariates are the parents of xj. And this connection is kind of really important in defining our GLM. And then for the undirected graph, so this is for the undirected graph, for the undirected graphical model, we once again have G equals VE, where V is again the set of P nodes, and then E is now a set of undirected edges. So in this case, the order doesn't matter. And we have then the key concept that's related, that's like the parents, is this notion of neighbors. So neighbors of xj is xk such that xk, xj is in E. And once again, remember that because it's undirected, what order it is doesn't really matter. And so if we think about the factorization, this was a little bit less intuitive in the case of undirected graphs. But it's connected through the graph structure through the edges and these potential functions. And we saw an example of that when you consider the multivariate normal, where these potential functions were like exponentials. So this was like a normalization constant, and then these were potential functions. And then in terms of conditional independence, we have that xj, it's kind of like what we saw in the DAG, but with the parents replaced by neighbors. And so there's no, if there's a conditional independence between xj and xk given the parents of, given the neighbors of xj and xk except for their two nodes, then there's no edge between the graph. And so if we then look at these parametric models, we learned that we could kind of define an overall model through the multivariate normal. So I'm going to use this notation MVN, and then we have this mu, or without loss of generality, I'm just going to assume that that's 0 because that doesn't really affect the overall graph structure. Dealing with like non-zero mu and zero mu, it doesn't really make too much of a difference. So we'll just focus on the case where that mu is 0. And the graph structure was encoded because we had that if you define this inverse covariance matrix, omega equals sigma inverse, then you kind of had this, you had that omega jk equal to 0 if and only if no edge between xj and xk. And then we can also generalize this to the GLM, but it's a little bit different from the DAG case because we can kind of define the conditional. We can kind of define conditionals for for each of the nodes, just like we did before. But it's hard to say how that relates to the potential functions and the normalization constant when you're dealing with like in the overall factorization. So if we wanted to generalize to GLMs, you can just say that for j equals 1 to p, we have that it's again very similar to what we saw for DAGs, but now the parents are replaced by neighbors. Sorry, I've got to remember to... Okay, and so so here the parameters are AKJ, and then we have only if XJ and XK is in the edge set. So those are the parameters there. Okay, and so obviously, like, I spent a while on that because we've spoken about that over the last few lectures, but that's how you can kind of define the models. And so our goal is if we have n independent samples from x1 through to xp, so this graphical model. So, can we, or how do we, one, like, estimate the parameters? And to estimate graphs. Okay, and so this is where that connection to the GLMs is going to be really important, because we've actually already learned how to do parameter estimation for GLMs, and that's what we're going to essentially use to do parameter estimation for DAGs and also for undirected graphs. So let's start with parameter estimation for DAGs. And so this is where, so we use the GLM connection. So we know that so for j equals 1 to p, we have this we know that the conditional okay, and so so we solve p GLMs to estimate parameters AKJ. So the parameters you're trying to estimate are these AKJs, and so you're just trying to solve these p parameters, and so you can think like a general sort of So general algorithm or framework is so if we just do for j equals 1 to p. Sorry, let me just so just to connect this back to the data, so just remember that our data here is x1i, x2i, up to xpi. Okay, and so we want to use that data to try to estimate these parameters akj. And then, so we can just say that for j equals 1 to up to p, we just have that so if we look at just akj, where k is the parents of xj, then we just solve GLM with response xj and covariates. Xk. Okay, and so remember that that just means that if this is where the knowledge of module 2 is going to be really important, then we have so that's going to be the arg min of akj, k in parents of xj, and then we just write the objective for the GLM. So it's going to be 1 over n summation, or let's give myself a bit more space. And then you just write that out as and then minus sorry, there should not be an xj in there. Oh god, that's bad. Sorry, let me start again. Sorry about that. Okay, so you just solve, and then you just kind of do this for each of your regressions. So let me just do a concrete example, just so that you so let's just do a concrete example. Okay, so here's a DAG. So we clearly have that. So v is here equal to x1, x2, x3, x4, and then we'll just say that the parents of x1 is just the empty set. There's no parents of x1. The parents of x2 is equal to x1. The parents of x3 is x2. And the parents of x4 is x1, x3. And one thing to note that, like, while I'm doing this, is that I'm assuming here that the graph structure is known, and so like that's why I'm talking about parameter estimation when the graph structure is actually known. And so that's quite that's quite different from what we're going to talk about later, potentially later in this lecture, and also and more specifically in lecture 20, in the next lecture. That's where we're looking at the case where the graph structure is unknown. But for now, we're focusing on the case where the graph structure is known, so we know what the parents are. That's the kind of the point. And in general, you may not know what the parents are, or for undirected graphs, who the neighbors are. So what we then have is let's look at then. So the parameters we need to learn are so the parameters here. You can kind of see that I can label them on this graph: A12, A23, A34, and A14. So the way we learn so A12, so then we can have A hat 12 equals to argmin of A12, and this is like you can use the GLM function in R to solve this. This is going to be A of A12 x2i minus x1i, and then we'll say A12 x2i. Okay, or I mean, to make it a little bit less clunky, I'll just say A12 x1i x2i. And as we've already spoken about, this is a convex optimization problem, and then you can certainly solve for A hat 23 argmin of A23 I'm sorry, that should be the other way around. This should be an x1 here. Yeah, so this should be an x2 because that's the parent that we're interested in. So this is, I guess, I'll just write this out too. So this is for x2, this is for x3, and then minus A23 x1i x2i x3i. Okay, and then for x4 we have two parents, so we're going to simultaneously solve for A hat 14 and A hat 34. And so that is argmin of A14, A34, and then A of x1i plus A34 of x3i, and then minus A14 x1i x4i, and then minus A34 x3i x4i. Okay, so that's just kind of showing you how you'd solve this in the case, and so you can see how that kind of scales quite easily for general P. So this is so let's see. So it's the parameter estimation for DAGs with known graph structure. Okay, so now let's look at parameter estimation for undirected graphs. Okay, and so we can use a similar approach with parents replaced by neighbors. So if our model is defined in terms of, so we're assuming once again that a model defined by conditional PDF in terms of the neighbors. So we have that, fj of xj given x neighbors of xj. And minus aj. Okay, and so once again, we do PGLMs. With xj as response. And neighborhood of xj as covariates. Okay. I'm not going to write out that for general because it's essentially the same as for the DAG, but we now replace the parents with neighbors. But I will do an example so that you kind of know what you need to do. General. So we're going to take the same essentially graph structure, but now with undirected edges rather than directed edges. Once again, we have these parameters. A12, A23, A34, and A14. We'll see that there's a bit of a complexity here that I'll talk about shortly. So the neighbors of x1 are x2, x4. The neighbors of x2 are x1, x3. The neighbors of x3 are x2 and x4. And the neighbors of x4 are x1, x3. And so once again, your data here is just going to be x1i, x2i, x3i, and x4i. Okay, and then so you essentially just solve these 4 different regression problems. I'll try to fit them, or let me do one at a time. So for x1, you're doing this GLM or GLM regression on a on your neighbors x2, x4. So you're going to get solutions for a hat 1, 2, a hat 1, 4. That's going to be augment of a1, 2, a1, 2, a1, 4. And you're going to get what we've seen before. So this is going to be a1, sorry, a1 of, it's going to be a1, 2, x2i plus a1, 4, x4i. And then it's going to be minus, so I should, to be clear, inconsistent, this should be a2, a3, and a4, which gives you the flexibility to potentially have different different GLMs if you want to, and then minus a1, 2, x1i, x2i, and then minus a1, 4, x1i, x4i. Then for x2, we're going to have a hat 2, 3, and a hat 1, 2. Okay, I'll do this one and then I'll stop, because hopefully it's the pattern is becoming clear to you now. A2 of a1, 2, x1i plus a2, 3, x3i, and then minus a1, 2, x1i, x2i, and then minus a2, 3, x2i, x3i. Okay, and you can, I'm just gonna leave x3 and x4. So this is an exercise. So hopefully, from what you've seen, there should be a pattern emerging here. So looking at this, some of you might notice that there's one, issue / challenge. And this is something that's specific to undirected graphs that we didn't see with DAGs. So note that you get 2 estimates. You get 2 estimates for each parameter. For example, we saw that, that a hat 1, 2, so you regress x1 on x2 and x4. And then you also get a hat 1, 2 when you regress x2 on x1 and x3. Because a1, 2 kind of appears in both of those. And so you're going to get the same thing for each of those, that for each parameter, you're going to get 2 estimates. In theory, like as n goes to infinity, so, in theory, as n goes to infinity, a hat jk, the 2 estimates should be the same. But of course, in practice, that doesn't always happen, because you don't have n going to infinity, and so like that. That's certainly something that's kind of challenging. And I guess there's a couple of things you can do. You can hope they are close. Hope the 2 estimates are close. Close and take an average. And that's kind of what people typically do in practice. But this is not kind of an ideal situation. This is born from the fact that the neighborhood relationship's not like it's a two-way relationship, so you can't kind of split them up. And it also is related to this notion that the factorization for an undirected graph is much more complicated than that for a DAG. And so this is an issue very specific to undirected graphical models. And so in the normal case, there's a way to overcome this. So if x1 through to xp are normal, we can use different approach. Essentially, we're going to parameterize things now in terms of the inverse covariance. So remember that the alternative way to parameterize things, if we have a multivariate normal, is that this is multivariate normal. Once again, I'm just going to assume the mean 0. If you subtract off the mean, then you effectively get the same thing. And so we know that omega equals sigma inverse represents parameters for the graph. Okay, and so this leads to this very this area that's kind of gained some interest recently, which is inverse covariance estimation. So we know that this omega represents the parameters of the graph, and so so we have that we know that x1, x2 up to xp is multivariate normal with mean 0 and covariance sigma, and so therefore we know that E of we'll say x tilde x tilde transpose is equal to sigma. So x tilde here is x1 through to xp, and so this is just remember, this is a p by p matrix that represents the covariance between the different x's. So you're kind of just taking an outer product and then taking the expectation. That's the definition. So this is just the definition of the covariance of x tilde. So what that means is, therefore, we can estimate sigma hat, or we can estimate sigma by sigma hat, which we're going to say is just the sample average of this. So this is 1 over n x of I transpose. So what here is like, I'm going to use this notation just to be, so x tilde I is just x1i, x2i up to xpi. And so this is clearly going to be an r to the p by p because it's just an outer product. So another way to think about it is that sigma hat jk is just equal to 1 over n. If you don't want to think too much about this this matrix notation, it's just xki. But you can write it in compact matrix notation kind of in this way. So this is just how you write it element by element. And then we clearly have that expectation of sigma hat jk is equal to sigma jk because of the because of the fact that we can, like, expectation is a linear operator, so you can clearly see that that's true. And therefore you can also show that, so by the law of large numbers, and we're assuming here that if if p over n, just to be clear, we're just assuming that the dimension is not too big compared to the sample size. So if p over n goes to 0, which will be the case in a lot of your simulations, but it isn't always the case, which is why I'm putting this condition in here. If P over N goes to 0, then sigma hat JK converges in probability to sigma, or another way to write that is that the probability that sigma hat JK minus sigma JK, and we're gonna just, if you take any of them together, the probability of the maximum over any JK pair, sigma hat JK minus sigma JK, that's going to go to 0 as n goes to infinity, for all delta bigger than 0. Okay, and so that's kind of nice. So therefore, how do we estimate the inverse? Then we just let that the inverse is just the inverse of the sample covariance matrix. And you can also see that, if sigma hat JK converges in probability to sigma JK, then the converse is also true. Omega hat JK converges to omega JK. And one thing to note is that you don't need to know graph structure to estimate omega, but if you know graph structure, then you can set omega hat JK equal to 0 if xj, xk is not in the edge set, because that's one of the things that we know. So you can imagine sort of doing this, where you do sort of a restricted estimate, where you only really do estimates where xj and xk is not 0. So this is a very useful thing that we're going to, it's potentially a pretty new concept, and we're exploiting for that. And this is only true for the multivariate normal. For the multivariate norm, we know that the graph structure is encoded through the inverse covariance matrix. And so if you parameterize your graph by the inverse covariance matrix, then you can kind of estimate the covariance matrix first, and then take the inverse to get the inverse covariance matrix. Okay, and so that's kind of a very useful concept. And so that's how we do parameter estimation. So when the graph is so the next question is and this is kind of the more challenging but probably more practically useful question. It's graph structure estimation. So it's like, what if the graph G VE is unknown? Okay. And so to begin with, we focus on the undirected we're going to focus on the undirected case. We may or may not time to get to the DAG case. The DAG case is actually extremely hard because when you have directionality associated with things and you don't know the direction of an edge, it makes it very difficult. You kind of get into causal inference types of questions, like, how do you know that x1 causes x2 rather than x2 causes x1. And that's extremely challenging from purely observational data. And so we probably, like, if we get time, I'll just talk at a high level about some methods to do that. But the sort of the more tractable question is if you, is the undirected graphical model case. So I'll just write that down. So for DAGs, if graph structure unknown, extremely challenging. Since you know, difficult to determine direction purely from observational data. Okay, and I mean, I'm just going to give you one example, just a very simple example here. If we look at p equals 2, let's say you have your data here is x1i, x2i, I equals 1 to n. Okay, and you know, so therefore there's just 3 possible graphs. You know, this is one possibility. This is the second possibility. And then the third possibility is like that there's just no edge between x1 and x2. Okay, and so if you know, if x1 and x2 are not dependent, if x1 and x2 are not dependent on each other, which is something we can test by just doing either regression of x1 on x2 or by kind of just doing a correlation if we wanted to if we knew that our data was like Gaussian, then we can conclude 3. But if x1 and x2 are dependent, it's actually impossible to distinguish between x1 and between the two models, between 1 and 2. And this gets to kind of a very core statistical issue about the difference between correlation and causation. Clearly, we know that there is correlation between x1 and x2, but that doesn't determine like whether x1 causes x2 or x2 causes x1. Maybe there's a confounder as well, but you know, we can't actually determine that. And so there are various things that people do to address this challenge. Like, you know, they might you know, assume, like, you may know a priori that if there is a correlation that x1 causes x2 rather than x2 causing x1, but without some additional information about the directionality of these relationships, you really can't say very much. So I'm not going to talk too much about estimating directed acyclic graphs here. As I said, if we get some time at the end of the next lecture, I might touch on it briefly, but I just want you to think through this example and kind of like convince yourself that it's kind of, you have this identifiability issue. You can't distinguish between those two models just based purely on observational data. Okay, and so so graph estimation for undirected graphical models. And this is kind of an area of significant interest because estimating graphs are something that's kind of quite important in a lot of areas of science, like in neuroscience, in biology, and so on, because the graphs kind of give a good visual representation of the dependencies between different features of interest. Okay, so in this case, I'm actually going to begin with the with the case where x1, x2 up to xp is multivariate normal with mean 0 and covariance sigma, and so we know that omega equals sigma inverse. Okay, and so the key relationship is that so graph structure is unknown. But we know that omega jk is equal to 0 if and only if no edge between xj and xk. And so this is really important because in G, which equals to VE. So therefore, this is kind of really, really nice because what that says is that, we can... This gives us a procedure, at least in theory, of estimating the graph structure. If omega jk is not 0, then place an edge between xj and xk. And if omega jk is 0, no edge between xj and xk. So, for example, let's just say you have, p equals 3, and your omega looks something like this, say. I'm just kind of making up the numbers here, but okay, then if this was your omega, then you could draw out your graph structure as well. This is going to lead to the overall graph structure that if this is x1, x2, and x3, there's clearly an edge between x1 and x2, so we have that omega 1, 2 equals -1, we have omega 1, 3 is equal to 0, and omega 2, 3 is equal to -2. So that means that you're just going to have a graph structure like that. And so in some sense, if you can just read off the zeros or the non-zeros of your inverse covariance matrix, that can tell you what the graph structure is. Okay, so that's really cool in theory, but in practice, you don't observe omega. Observe omega. All that we So we observe x1i, x2i up to xpi. And this is where what we learned in the what we just learned about parameter estimation is useful is that we can construct estimate omega hat based on data, where we know that sigma hat is given by this overall where you imagine sort of putting that in a p-dimensional vector and then putting it together like that, and then omega hat is equal to the inverse of that. So omega hat jk will never be zero. Will never be zero unless you force it. So in general, even though the population, so we know that as n goes to infinity, omega hat jk converges to omega jk. So converges in probability to omega hat jk. So, but for finite n, and this is finite n, omega hat j minus omega jk is not zero, but hopefully small. Okay, and so omega hat jk, so if omega jk is zero, omega hat jk is not zero, but hopefully small. Okay, and so one approach is to threshold inverse covariance matrix. And there's been a fair bit of work on this too. So the idea here there is that if omega hat jk is if the absolute value of that is bigger than some threshold t, then omega hat jk remains the same. But if omega hat jk is less than or equal to t, then omega hat jk equals 0. And so in the next lecture we'll go into this in a little bit more detail, but and I'll give you kind of a concrete, that sort of 3-node example that I spoke about. We'll talk about kind of what actually happens in practice with that. And then we'll kind of we'll kind of go from there. And then the key question is then how do you set the threshold t? So how do you set this threshold t? Like how do you set this threshold t? And, are there other approaches that might do better? Okay, and so that's something we're going to talk about in the next lecture, and I just wanted to kind of give you a hint or something to think about. Think about Module 3 and the lasso. Because remember, that's where you kind of try to set things, you try to set things to 0, and rather than acting as like a hard thresholding, which is what we're doing here, it does a soft thresholding. And we're going to be doing that both in the case of this inverse covariance matrix, and then also in the case of we're gonna do that also for general GLM settings as well. So that's something to just think about before the next lecture, and that's going. And then we're gonna go into this kind of estimating undirected graphical models in more detail then. Okay, thanks very much for that. Have a good rest of your day.